Hi, this time we're going to find a set of vectors in R4 spanning the solution set of a system of linear equations, just as the one that we are presented here. As usual, what we want to do is to obtain an equivalent yet simpler system. And how do we do that? Well, by the usual row reduction process. But let's indicate that. First thing that I want to do is to find a simpler yet equivalent system. So what is it I'm going to do to present this system of linear equations in the form of an augmented matrix? I'm going to make use of the syntax of a matrix to manipulate the entire system. So I get something like this. I have 1, negative 1, 1, negative 3, followed by 0, then 5, 2, 1, 1, 0. And that takes care of the W part, the X part, the Y, and the Z, and that allows us to make that interpretation. Okay, so next operation, row reduction, as usual. We already have a pivot, so we can use the regular Gaussian elimination process. So we have R2, we subtract 5 times row number 1, and thus obtaining the following matrix. 1, negative 1, 1, negative 3, 0, 0, 7, negative 4, 16, 0. Okay, now out of that one, right, we're going to turn this into a pivot, right, by multiplying the second row by 1/7, and we get something that looks like this. Pretty much. We have 1, negative 1, 1, negative 3, 0, and then followed by, well, on the second row, 0, 1, negative 4 over 7, then 16 over 7, 0. Okay, now we continue with the reduction process. So in that case, we have to row 1, I add row 2. So I already have a pivot here, and I want to eliminate this one. So now it turns like this, into 1, 0, 3 sevenths, 5 sevenths, 0, 0, 1, negative 4 over 7, 16 over 7, 0. And with this I stop. This is the row reduced echelon form of the matrix. Time to reinterpret. So time from moving from the syntax to the semantics. What does this mean? Well, of course, this means that the system may be seen in this fashion. This being the W, the X, the Y, and the Z, the columns encoding the coefficients associated with that sum. You have that W is equal to negative 3 sevenths of Y minus 5 sevenths of Z, while X is equal to 4 sevenths of Y minus 16 sevenths of Z. Okay, so once we have it in this fashion, right, let's recall what we're trying to do. We want to determine a way to generate every single solution based on based on the computations that we have just performed, and we can do it in the following way. Determine the generating set, in this case, or the spanning set for the solution. Well, now we can say something like this. If you're given a vector, right, of the form W, X, Y, and Z, Well, this one is a solution if and only if these two equations are satisfied. In other words, if and only if that vector w, x, y, z is equal to the vector negative 3 over 7, y minus 5 over 7, z. Then on the second entry would be 4 over 7, y minus 16 over 7, z, y, and z. Now, it's not so difficult to see that from this vector we can separate it into two terms. One being factored by y, and the other one being factored by z. Negative 3 over 7, 4 over 7, 1, 0. Plus z, negative 5 over 7, 16 positive over 7, 0, 1. Negative, I'm sorry, negative for this. But what is this saying? Well, this is saying that no matter what solution that we provide, it has this format, right? For arbitrary y and z. So, a solution is a linear combination of these two vectors, negative 3 over 7, 4 over 7, 1, 0. And the vector negative 5 over 7, negative 16 over 7, 0, 1. And with this we're done, because what we have just found is a collection of vectors, right, spanning the solution set of the desired system of linear equations. And with this we finish. See you next time.